All right. So where we left off, states of matter. This is essentially the middle portion where we left off, where I talked about these cooling and heating curves. So we see essentially a change in state and a change in temperature. And these are the portions of the curve. So portions 1, 3, and 5 are all different changes in temperature, while portions 2 and 4 indicate changes in state. So we talked about this, and then I gave you guys two equations, which is Q equals N delta H and Q equals MC delta T. So Q would represent the heat, N represents the number of moles, and delta H represents the enthalpy, the change in enthalpy. Specifically, the enthalpy of fusion or the enthalpy of vaporization. The Q over here, MC delta T, represents the equation that corresponds to the values of M corresponding to mass, C corresponding to the specific heat of whatever compound we are talking about, and delta T corresponding to the change in temperature. So let me state this right here. This is going to be the enthalpy of, let me actually shrink this. Oh, did not want to do that. I hope you don't want to click that for some reason. The enthalpy of vaporization or the enthalpy of fusion. So this delta T actually is going to represent the temperature of the initial sample minus the temperature of the final sample. So Q, as I said, is heat, thermal energy, and mass. It's going to be usually in grams or kilograms. Remember, if you are using a specific C value, you need to have your mass correspond to that C value. We have temperature, which is going to be in Celsius. So make sure we use degrees Celsius. N is the number of moles, and C is the specific heat. So here are examples of the equations. We have state change and we have temperature change. So in each of these cases, we are using water as our compound. So if we go from 20 degrees Celsius to 50 degrees Celsius, we will only use the equation Q equals MC delta T because we only have a change in temperature. We do not have a change in state. If we are going from 100 degrees C to a gas for H2O, we will use the Q equals N delta H, and that will be delta H of vaporization. Because we have a state change, however, we do not have a temperature change. When we are going from negative 20 degrees Celsius to 150 degrees Celsius, we actually need to use both equations because we are undergoing multiple state and temperature changes. We would calculate the Q value for each of the individual portions of this and then add them together to find a Q of the entire compound or change of state. So let us do a problem. So let's ask how much heat is required to convert (422 grams of liquid H2O at 23.8 105 degrees Celsius into steam. At 150 degrees Celsius. So here is our question. And this is a question that is essentially going to include all of the equations. So let's see what we have here. Our equation is asking for how much heat. Oops, I do not want that. So I want to know the heat that is required to convert 422 grams of liquid H2O at 23.5 degrees Celsius into steam at 150 degrees Celsius. So I did underline a lot here, but it's not really that much if you think about it. So we have a Q value here. So we want to know Q. We have a mass right here. We have a state here. So this is our initial state, and here is our final state. Here is our initial temperature. Here is our final temperature. Here is our compound. So we have T initial. Yeah, let's call it T initial instead of T1 and T2. T final. So the initial temperature is 23.5 degrees Celsius. The final temperature is 150 degrees Celsius. We also have a state change. We have H2O in the liquid state going to H2O in the gaseous state. What other information we have? We have the mass, which is 422 grams. And we want to find out the total amount of heat. So let's call this tote. So I pretty much provided nearly all of the information we have here. And so we need one more piece of information. We need the equations, well, actually two more pieces of information. We need our equations, and we need any other constants that might be required for those equations. So based on the previous information I gave you, we actually have a state change and a temperature change. Therefore, we need to use the equations Q equals MC delta T. And we need the equation Q equals N delta H. And specifically, we need the delta H of vaporization. So after you pull all the information out of a question like this, now you want to figure out what types of equations you would use. And these are the equations right here. And then looking over these equations, we want to figure out what other information we would need to solve for these equations. Well, we see that we need the specific heat, and specifically, we need the specific heat of a liquid. Well, actually, we need the specific heat of, we need two specific heats. We need the specific heat of a liquid, and we need the specific heat of a gas. Because not only are we going from a liquid to a gas, we are then raising the temperature of that gas to 150 degrees Celsius. So we need the specific heat of the two different states as well. So keep that in mind whenever you do an equation like this. Every state has its own specific heat, and that makes sense because think about it. Specific heat is, in a way, the measure of energy required to raise the temperature of a compound. And so a liquid would have stronger intermolecular forces than a gas, and therefore the ability to raise the temperature of something like liquid water would be easier or less easier to do than raise the temperature than something as steam, which is gas, which is already moving around quite rapidly and doesn't have much of a hindrance in the form of intermolecular forces between the individual gaseous molecules. Does that make sense? So it looks as if this equation I have, or this answer key I have, does not do this problem correctly. So let's actually pull the information we need from Google. So let's look at the specific heat of water at both the gas and liquid state. I believe I wrote it down last time somewhere, but I don't have it in front of me right now. All right. So the specific heat, let's see if this is in the right units I want. Joules per grams per Kelvin. Yes, that is correct. So the specific heat of water in the liquid state is a number that may be useful to memorize or just recognize. 4.184 joules per grams Kelvin. So I actually made a wee mistake here. We actually want specific heat to be in Kelvin. So we need to make a conversion of Celsius to Kelvin. So keep that in mind. Then the specific heat of water in the gaseous phase. Let's see, that is 2.080 joules per grams per Kelvin. We now need to do a conversion. So actually, let me pull this down so we can keep things neat. So we need to convert the Celsius to Kelvin. Does anyone remember the equation for that? That number, that 273.15? Alrighty. So whenever we do any sort of conversions, these typical number we use to go from Celsius to Kelvin is 273.15, and that means that at 0 Kelvin, or at 0 degrees Celsius, we have 273.15 Kelvin. So if we go from 23.15, we have, or not 23. We have 296.65. We simply added that 273.15. And if we want to go from that 150, again, 423.15. All right, so Kelvin. I want to note that Kelvin is not degrees Kelvin, it is simply Kelvin. There is Kelvin is an absolute temperature, therefore it does not have degrees. So at this point we have all the information we need. So let's actually put things together at this point. The first thing we need to do is we need to find the Q of the temperature from the 23.5 degrees Celsius, or the 23.5. We're actually going to need to do a few more conversions. To 100 degrees Celsius. From 100 degrees Celsius, we are going to have a state change from a liquid to a gas. And then we need to go from 100 degrees Celsius of gas to 150 degrees Celsius. So we need one more number here, and that is 100 degrees Celsius in Kelvin. So this is all the information we need to complete this problem. And it's a lot, because this is a pretty big problem. It is taking into account multiple state changes and multiple temperature changes. So actually, let me put this on the top. This probably would have been the first useful piece of information. Alrighty. So let's get to work on the first step. So the first step, we are going from 296.65 Kelvin to 373.15 Kelvin. So let's start this out. Let's call this Q1 equals MC delta T. We will rewrite this as the mass. So we have mass somewhere here. Where are we? 422 grams. So 422 grams. We need the specific heat of the liquid state, because we are currently in the liquid state. So we are going to multiply that by 4.184 joules per grams Kelvin. After that, we need our delta T. So we need our T initial. So our initial T is 296.65. Minus the T final, which is 100 degrees Celsius, or 373.15. And that is everything we need for Q1. So Q1, we went from a temperature change. And this is the first thing we do. So the next thing we need to do is state Q2. So what is Q2? Well, Q2 equals N delta H of vaporization. Because remember, at this point, we are going from a liquid to a gas. Because we are going from 23.5 degrees Celsius to 100 degrees Celsius. So keep that in mind. So let's write this equation down. Q2 equals, well, we need the number of moles at this point, and conveniently, or rather non-conveniently, I did not write that down. So let's solve for the number of moles. So we have 422 grams of H2O. And if we have 1 mole of H2O, that is approximately 18.02 grams of H2O. We punch that in our calculator, and we get 23.4 moles H. Let me try to shrink this a little bit. H2O. Alrighty, so this is our final piece of information we need, the 23.4 moles. Make sure I use the correct specific heat. This answer key might be really screwed up because it is saying it should be using, hold up, I'm pretty sure it's Kelvin. Joules per grams per Kelvin. I'm getting 2 different specific heats, and they're the same. I'm going to say it's Kelvin. All the books are saying it's Kelvin, but for some reason I'm seeing this thing saying joules per grams per Celsius sometimes, so something weird is going on here. I'm pretty sure it's Kelvin. All right, I'm going to stick with Kelvin. So, Q2, we need our N, and our N is 23.4 moles, so 23.4 moles of H2O. And now we need to multiply it by that delta H value, or the delta H of vaporization. Did I give you that value? Nope, that is another piece of information we need. So the delta H of vaporization, so let's look that up. So the enthalpy of vaporization 40.65 kilojoules per mole. So 40.65 kilojoules per mole. So this is our Q2. Now at this point, we have converted all of our water from the liquid state into the gas state, but we are still at 100 degrees Celsius. So we need one final equation to put this all together, and that is Q3. So Q3 will equal the MC delta T, but specifically we will need the C, or the specific heat of the gaseous state, and this one would have used the liquid state. So let's write that down. Q3 equals 422 grams multiplied by the specific heat, which I know is 2.080. I think that was it. Yep, 2.080. Line there. Joules per grams Kelvin. And finally, we will multiply by the temperature change, which is T initial, and the initial temperature is 100 degrees Celsius, which is 373.15. So 373.15 Kelvin. We're going to subtract from T final. And the T final is, where are we? The T final is 423.15 Kelvin. And so we now have all of our information in our three equations. And what we need to do is we need to take Q1 plus Q2 plus Q3 equals Q2. So simple. Let's start with our Q1. So let me punch this in. Let me open up Wolfram Alpha real quick. So 422 times 4.184 296.65, 296.65 minus 373.15. So this comes out to a very, very big number. We have negative 130.5072. .072 joules. So this is not with the proper number of significant figures. The proper number of significant figures would be right here. So we could joules, or let's see, 1, 2, 3, -1310 kilojoules. So this is going to be our first Q, or no, this should be our Q1. Why do I have that in Q2? Let me make some space here. That is our Q2, not our Q1, not our Q2. So let's do our Q2 now. So our Q2, really simple. So this is just one basic multiplication. We are going to do kilojoules is going to be what we end up with. And the reason I converted that to kilojoules is because you'll notice that the delta H's are in kilojoules per mole, and so when we add everything together, it'll be in kilojoules rather than joules. We won't have to do an unnecessary conversion. Alrighty. What do I want to do now? So 23.4. Multiplied by 40.65 equals 951.21 kilojoules. And finally, let's do the last one. The last one is 422 multiplied by 2.080 multiplied by 373.15 minus 423.15. And I thought about it for a moment, and I just realized why for these equations, you'll see the specific heat used is joules over grams per Kelvin and joules over grams per Celsius. And after thinking about it for a moment, it turns out it doesn't matter if we are in Kelvin or Celsius, because to go from Kelvin to Celsius and Kelvin to Celsius to Kelvin is a one-way direct conversion. We are just adding a number to the other number, 273.15. We are either adding or subtracting it from the Celsius or the Kelvin to go one way or another. And therefore, when we take the difference of the two numbers, it won't matter. If we are in Kelvin or Celsius, the difference between the two numbers will give you the same number. And therefore, we technically, for this problem, did not need to convert from Celsius to Kelvin. But it is still good practice, since a lot of these problems do use Kelvin and require it. Just make that note. Is that Q3 that you gave right there, that -135? was for Q1. You got 1, 3, 5. Oh, that means I messed up somewhere. Oh, you are right. You are correct. So I'm seeing negative 1, 3, 5, 0.072. 0.072 with 4 sig figs, which will come out to 1, 3, 5, 1, 0, 0. And that should come out to 1, 3, 5, kilojoules. All right, that fixes that up. Awesome, thank you, thank you. So that's Q1, we have Q2, and Q3 is the last one we need. So let's see. So 3.15, 423.15, 2, and 422. And this is giving us a value of negative 43888 joules. And let's convert that into kilojoules. We have 3 sig figs for the least. And so this is going to be negative 4.3. So let's see. 0.8, or rather 0.9 kilojoules. This actually should be with sig figs. And let's see, where else are we? With sig figs, just 135. Just 3 sig figs there. All right. Are we all on the, so did I lose anyone at this point? Because I know I've been mumbling and bumping around a little bit, but are we all on the same page here? Awesome. So at this point, we have 3 values for our Qs. We have our Q2, we have our Q3, and we have our Q1. Now I want to note that if you guys were to do this on any sort of standardized test, do not use this rounded number here. Do not use this rounded number. I'll use that, let me round this as well. 951 kilojoules. So do not use this rounded number. Because these numbers were all rounded, Q1, Q2. Because all these numbers were all rounded and we are not finished with the math, if we use these rounded numbers, we will introduce what is known as rounding errors. We actually want to use the big number that we generated when we do this. So let us take a big number And actually, if you do this on a calculator, it will be a bit easier. So we will take this number. Where is our cube 2? We will take this number. And we will take this number. Ooh, I did not want to copy all of that. Let's see. Whoops! One more mistake I made. I think I didn't put in the show it in the general equation. Where is it? Where is it? Yes. So, although we will get the same value, its sign will be incorrect. I was noticing our values were off by sign. So final minus initial. So apologies for that as well. Final minus initial, not initial minus final. This will not change anything except for the sign. So our Q1, if we flip this around, it becomes a positive. Our Q2, looks like someone joined the team. Looks like we might get another person to join our meeting today. So that's that. Let's flip this one as well. Because the sign of these Q's actually states something. So now we have positive Q's for all of these, which makes sense. We also need to do a conversion because I have not converted these yet to convert these joules into kilojoules. So we take the decimal place and move it 3 points to the left. So 1, 2, 3. So 135.072.072 kilojoules plus 951.2 kilojoules plus, we're going to take this 3 points to the left, 1, 2, 3, 43.888 kilojoules. And so these are the values we have right here, and all we need to do is add them all together. So let me do that. comes out to 1,130.160072 kilojoules. Oops. There we go. And let's actually use significant figures. We will have 3 significant figures total, and this will come out to 1,130 kilojoules. So that was a very involved and very long problem that takes into account every single step of the process in these types of problems. Where did my chat go? Are there any questions on this one? Would you like me to do 1 or 2 more simplistic ones where we only do either a state change or a temperature change? Or do you think this example is complete enough for everyone? All right, let's do another one. All right, let's say we have H2O. And we want to take H2O from a temperature of, let's say, 10 degrees Celsius. Or rather, let's do something better. Let's do 70 degrees Celsius to 8 degrees Celsius. So this is all the information I'm giving you, and I want to know what will be the heat that is either absorbed or emitted. So maybe another part of the question, is this a exothermic or endo? So before we even do this question, this problem, do you guys think this is an exothermic reaction or an endothermic reaction? Is heat being absorbed or is heat being released? So that is correct. It is an exothermic reaction. Heat is being released because we are going from a high temperature to a low temperature, meaning heat needs to be expelled somehow. And because of that, our Q is going to be a negative. So note that if we have a negative Q, so if we ever don't know, Q positive equals endothermic, and Q negative equals exo. Because if Q is negative, that means that heat is being released. So therefore, the Q is going to be decreasing. If Q is positive, that means heat is going to be absorbed. That's why I said, I caught right up here that the negatives for our Q's didn't really make sense all of a sudden, because since the temperature is rising, that means heat was being absorbed. So all of our Q's based on this should be positive. And so just keep that in mind. Little small things like that could help you. You make a small mistake on an equation and you get a value that just doesn't make sense. Like if you have a positive sign and you know it should be a negative sign, realizing if the reaction is exo or endothermic could help you out in that regard. So let's see, what information do we need here? Because we are only doing a temperature change, we only need the formula of Q equals MC delta T. And let's say I did not give you a mass. Let's say we are doing 100 grams of H2O. So we need a mass, we need the specific heat, so the specific heat of water, and because we are in the liquid state, the specific heat of water is 4.184 joules per grams Kelvin. But because this formula right here is going to break down this delta T to T final minus T initial, we are actually going to not care about the temperature for this type of problem. And by the temperature, I mean the units the temperature is in. Therefore, we can keep our units in Celsius. So we would say that T initial equals 70 degrees. And T final equals 8 degrees. So no, we are going from 70 to 8. So that's why we have the units that we have here. So let's use our equation and plug our values in. And note that units like the CL, which is a constant, CL is the specific heat of water in the liquid state, will be given to you. So you won't really have to worry about that. And so let's, because we don't care, degrees Celsius will work here as well. So Q equals, the mass is 100 grams multiplied by the specific heat, which is 4.184. Joules per gram Celsius. Multiplied by the temperature change. So the final temperature is 8 degrees Celsius. And the initial temperature is 70 degrees Celsius. So at this point, we have all the information we need, and all we need to do is plug that into a calculator, or in my case, Wolfram Alpha, and let's see what we get. So 100 times 4.184 multiplied by open parentheses 8 minus 70 close parentheses. I am given a value of negative 25940.8 joules. And just so you know that it's joules, we see the grams cancel here, the grams cancel here, and the Celsius cancel in this regard. And that's why we are left with joules. And if we want, we can convert this into kilojoules. So we take this decimal, bring it 3 points to the left. 1, 2, 3. Negative 25.9408 kilojoules. And let's see for our significant figures. Well, let's actually say that there is a decimal point here, because if we use that 100 for significant figures, ooh, it looks like, let's put a decimal point here too. Well, it doesn't seem like it really matters. We will have one significant figure regardless of our decimal points because of that 8. So that one significant figure will turn this into negative 3 kilojoules. So that will be our final answer for Q. Any questions on this one? Let's do one more. Let's do one with state change this time. So let's say we want to freeze some water. So let's say we have some H2O. And our H2O is at 0 degrees Kelvin or Celsius currently. But it is in the liquid state. We want to go to negative, let's say, 20 degrees Celsius to the solid state. So we are going from, no, let's actually not do that. Let's go to 0 degrees Celsius in the solid state. So we are going to do H2O liquid to H2O gas, or solid rather. I need to turn off notifications. All right. So we're doing a state change right here. And because we are doing a state change, we do not need our Q equals MC delta T. Instead, we need our Q equals N delta H. And specifically, we need our Q equals N delta H of fusion. But I want to note, because we are going from the liquid state to the solid state, this delta H of fusion needs to be a negative. So I think I had the delta H of, nope, I don't have the delta H of fusion. So the enthalpy of fusion. The enthalpy of fusion for water is 333.55. This enthalpy of fusion is in joules per grams. Right. So the enthalpy of fusion for water is 6.0 kilojoules per mole. There we go. And let's again say we have 100 grams. So we need to do one thing. We need to take water from grams to moles. So we'll take 100 grams of H2O. Let me change to red. Grams of H2O. So 1 mole of H2O is approximately 18.010. I think that's what it is. We actually wrote it down somewhere. 19.02. Grams H2O. So let's do that. So 100 divided by 18.02. Give us 5.549 moles H2O. So we have the moles of H2O, and now we are just going to use our delta H of fusion and combine these two values. So we will do Q equals, let's see, 5.549 moles of H2O. Then we are going to multiply it by our constant, which is diffusion, 6.0 kilojoules per mole. And we see that moles cancel out, leaving us with kilojoules. Maybe punch this in the calculator. So 5.549 times 6 is 33.294. And so, let's see, we had 1 sig fig, so this will round out to 30 kilojoules. Honestly, I did not mean for these two values to actually equal the same. I swear I just made these numbers up. So it's sort of interesting that both of these values are interesting. So, but on another note here, the energy to essentially go from essentially this 70 to 8 degrees Celsius is the same energy required to go from H2O in the liquid state to H2O in the solid state. It's different. We're losing energy here and we're absorbing energy here, but nonetheless, it's the same value. Oops, I made a mistake. This should be negative. So we have negative 6.0 kilojoules per mole. And if we use that value right here, this is going to be negative. And again, I was like, why is that positive? So yes, make sure to always look at your units. You'll a lot of the times look at your units and you'll catch a mistake that you made, like I just did. So we see that in both of these cases, we are losing energy here. We are giving up energy to the surroundings in both of these cases. That's why the kilojoules or the energy is negative. But it's also interesting to note that a temperature change from 70 C to 8 C is equivalent to a state change of liquid to solid. Just an interesting thing to note. And I swear I just made these numbers up from the top of my head, so it's sort of interesting that they sort of coincide. Anywho, let's see. I think that's all I want to talk about for today. Are there any questions on any of this? Alrighty, if there are no questions, that is all I really wanted to talk about for today. So next week on Monday, so we'll have another lecture on Monday. We will finish this off by essentially talking about gases. So we should. Monday is going to essentially be gases, and then thermo will be the last thing you guys talk about. Thermo is actually going to be really short because a lot of the things I'm talking about here are thermodynamically related. This entire thing we did today is essentially a portion of thermodynamics. So the thermodynamics section is going to be very, very short. We won't have too much, or thermochemistry rather, not thermodynamics. The thermochemistry portion will be very, very short compared to this. We only will talk about one or two more things other than what we talked about here. So there isn't really much more to talk about at all. We are pretty much done at this point. So you specifically want more problems like this specific problem we did here? I would say state change problems, state and temperature change. And probably the one YouTuber guy, the organic chemistry tutor, is really good. He does a lot of example problems, and he has stuff over several years. Although I would be a little bit careful when watching some of the videos because there are mistakes made, and so I would recommend if you do watch those videos to go to do the equations along with them. Because just like I make mistakes, other people make mistakes. Any questions on anything else for anyone?